the private chat. Anyway.
So maybe if we tell people to go there, they can do a live chat. Okay, good morning, everyone. Today is February 29th, 2020. So we're discussing problems with getting into the conference. So apparently you do need to click on the link that's in the email. Try just typing in live.naturalphilosophy.org, and that may or may not get you where you need to be. So apparently, because we had someone try and get in this morning, and apparently they couldn't get in by just typing in the URL. But apparently, so if you want to join the live room and you don't have the email, you could try this, and hopefully that will get you into the right place. Although I thought I tried this morning just typing it in myself, live.naturalphilosophy.com. Well, not com, it's org. Live.naturalphilosophy.org. And it looks like it got me to the correct link. So yeah, it looks like it did. So, but that's the same link that Bob just sent me, the one ending in G42. But in any case, if Dennis, if you're watching, if you'd like to join us in the live room, you can try this URL here. So I'm not quite sure why it wasn't working for you, but apparently it works better if you use the email that we send out. So hopefully that'll help some people. All right, so what's on people's minds? So Bob has got a paper here in Vixera. Let's see what this paper is about here. It's called Something Rotten in the State of QED. So let's see, let me share that. See, we've got James here.
Hello.
Good morning, James.
Hi, James.
Hello. Hi, Ian. Good morning.
I'm to you, James.
So, Bob, you got this paper here. Something is rotten in the state of QED. You want to take us through this?
Actually, no.
No?
Not my paper. It happened to come my way. I figured other people on the natural philosophy would probably receive the same information and just put it up if somebody wanted to discuss it. I've read the abstract, breezed through it a little bit, seems interesting. I followed some of the references to the math that they were saying is kind of screwy and yet acceptable, quote unquote, in physics today. And they're right, it is kind of screwy. But I'm not, I'm not the author, and I'm not really technically skilled on QED to be able to competently discuss it. But I wanted to point it out to others in case they've read it, or in case somebody's interested in QED and potentially problems with it. I thought that was a good place to start.
Well, how would you describe what the heck QED is it? Because I'm not exactly sure myself.
Well, right there on equation 1 that you're showing is part of the problem. Part of QED is you try to calculate anything and you always come up with infinities, but you can deal with infinities depending on how you do sums and whether you subtract infinities from both sides, etc. And there in equation 1, they're showing the sum of n equal 1 to infinity, 1 plus 2 plus 3, etc., is equal to minus 1 over 12. And they go go
Well, that makes a
through.
lot of sense.
I know, but there's a reference there, reference number 2, and if you look at reference number 2, it's Euler or some other famous person explaining why that is the case, that the sum of the integers is equal to -1 over 12, and apparently that's used as part of a QED calculation, which is bizarre. I mean, that's not correct.
But what are
And
they
yet,
calculating in QED? Now, I know that QED, has something to do with Feynman diagrams or something. Maybe we should just start there. Let's look in the
well, the big thing that they're calculating is the magnetic moment, I think, of the electron, or the anomalous magnetic moment. And one reason why they say QED is so good is because it calculates that number very precisely. And yet this author is in part showing, well, the mathematics for that is very screwy. It's not really valid mathematics.
let's see here. I'm going to look up quantum electrodynamics. There you go. The source of all truth, Wikipedia. But I like Wikipedia because it's kind of the source of truth that you might have some chance of understanding, since it's written by people. But they say, in particle physics, quantum electrodynamics is a relativistic quantum field theory of electrodynamics. In essence, it describes how light and matter interact, and it's the first theory where full agreement between quantum mechanics and special relativity is achieved. So once again, we're here, they're supposed to explain how light and matter interact. And then they have this Feynman diagram over here, which I'm not terribly sure it's not supposed to be really explaining anything. Kind of looks like a cartoon to me. In technical terms, QED can be described as a perturbation theory of the electromagnetic quantum vacuum. Richard Feynman called it the jewel of physics, and extremely accurate predictions of quantities like the anomalous magnetic moment. So that's the constant that you're talking about, right?
Right, yeah.
Of the electron and the Lamb shift of the energy levels of hydrogen. All right, well, there's a couple interesting topics here. So what do they say the quantum vacuum is? Quantum vacuum state, because we always had this question of what is the vacuum? So it is the quantum state of the lowest possible energy. Generally, it contains no physical particles. 0-point field is sometimes used as synonymous for the vacuum state of an individual quantized field. So they say generally contains no physical particles, but they also says by no means a simple empty space, according to quantum mechanics. So what is it? Is it empty or not empty?
Not empty.
But they say instead contains fleeting electromagnetic waves and particles that pop into and out of existence. Well, isn't that magical? Now, this week in the email chains, we've been having this discussion actually about this particular topic. So Cornelius, who often joins us, feels that space is not filled with physical particles, and everything is, say on tension waves, or at least waves here. I think we have some other people who might also believe that that magnetic waves are somehow fundamental. But we have this this thing that mainstream calls, which is the quantum vacuum state, which is not empty but contains something, right? And
Yes, they actually will. You'll see references where they talk about the energy content of vacuum,
which is apparently just humongous, right?
I don't have the other people's estimate, but my estimate is that about 88% of the quanta in a 0 Kelvin state is vacuum, and so it's literally teeming with quanta. It's not empty space, in my view.
Yeah, I
Now,
think that's a view, and I would agree with you.
Now, if I may comment while you have the diagram up there, Franklin, on the upper right of where they show the vertices, there's two yes, that one. Two vertices in that Feynman diagram there. When I
Yeah, we got one
calculated
here, one there.
when I calculated Planck's constant derived from first principles, it turned out it was convenient to define what I called an elemental action, and the elemental action divided by alpha gives you Planck's constant. Okay, so what that implies is that there are well over 100 events going on in what might be called a one Planck constant event. And so that these vertices are hiding in plain sight, in my opinion, the two vertices of the diagram that you're showing.
What are these
They're
vertices?
hiding, most of the physics is hidden in the vertices there.
Say, James, when you do your calculation of Planck's constant, do you also get the units? Because I have read some papers
Yes.
that say the current units of Planck's constant is not correct. There should be an additional time unit.
Exactly.
And I'm wondering if you get that
my
time unit or not.
No, my calculation of Planck's constant has the units of joule seconds. It's a product of an energy term and a time term. And that's why Planck's constant is not a pure quantification of energy, as is done in binary mechanics, independent of time and frequency considerations, which is, in my opinion, a major advance.
It's what's called action. Energy by time is action.
Exactly. It's nice that Franklin can show these papers. I would remind Franklin that it would be convenient if his browser allows it just to magnify the page a little bit so that the print is larger.
Oh,
on the
yeah,
screen.
we can do that, I think. Zoom. We can.
Yeah, just zoom it up once or twice. Yeah, there you go.
But I was wondering, does anyone actually understand what this Feynman diagram is and why did they think this is significant? Now, according to the description here, so we've got a positron, which is the E minus, and an electron, which is E minus, coming together, producing the gamma ray, which is the blue little squiggle. But then it produces a quark and an anti-quark and radiates a gluon. It's like, and I'm going, what? Now, as far as I know, you get a positron, electron together, you get a gamma ray. I get that part. I don't know about this. I don't know anything about this quark, anti-quark, and this gluon, which, as far as I'm concerned, are three things that just don't exist. So I was wondering if anyone can chime in on, what this actually means for someone who understands QED. Nobody? Are you as mystified as me by this diagram?
Well, they're using the particle interaction model to define forces in physics. I don't use that model. I use a purely mathematically defined model when things are fully quantized. And as I say, like what they do is there are three vertices. If you count the gluon coming off there are three vertices in this diagram, and most of the physics is occurring there, and it's completely hidden in plain sight. And the anomalous magnetic moment, for which someone, one or more people received the Nobel Prize, by the way, is, in my work, nothing more than an experimental artifact, because the constituents of the electron themselves can act as potentials, either magnetic if they're an L-type bit, or electrostatic if they're an M-type bit, and that's going to affect your measurements. So this anomalous magnetic moment is really sort of silly. It's basically an experimental artifact. And if you take that out, you get the Bohr magneton for the magnetic dipole moment of the electron.
Yeah, there are a lot of things to look at in this particular thing here. Let's get back to QED. So that's Feynman diagrams, which according to that previous reference was supposed to be some way of expressing how the humongously complex equations in a diagram, though I'm not terribly sure that that works. And we just talked about the quantum vacuum, which is empty, but not really. Let's see, let's go back to the quantum vacuum here. Where did I see that? That's in quantum electrodynamics. Well, let's look at this anomalous magnetic moment. Anomalous magnetic dipole moment. So what is this? It's a contribution of effects of quantum mechanics with loop to the magnetic moment of that particle. Now that doesn't make any sense. The magnetic moment, also called magnetic dipole moment, is a measure of the strength of a magnetic source. So what's so anomalous about it? The Dirac magnetic moment.
It varies from the Bohr magneton. And by the way, you can derive the Bohr magneton from first principles with full quantization without the G factor, the so-called gyromagnetic factor, and without that factor of 2 in the denominator in the equation you're showing right now in the middle of the page on the left. So what we're looking at here is basically we're sort of going back in time. It's like we're anthropologists and we're going back to see what physics was like a century ago, or in the previous century, I should say, 20, 30 years ago or more. And it's sort of interesting to see what they were doing 20, 30, 40 years ago. But basically, this is like a history lesson. I mean, there's not a whole lot of science there, okay? In my opinion, in my humble opinion, or not humble opinion.
Now here's a thing where they have the something that's experimentally measured value to more than 10 significant figures is, all this claim that they make. Although I think the last time I actually looked at that experiment, what they're actually measuring is some frequency to like 1 significant figure. Apparently if you can measure this frequency and then which I can believe they could do, then you can put it in some calculation which calculates this value to 10 significant different digits. So I'm not 100% sure that's true, but that's kind of what I concluded, which means that this whole thing about 10 significant, experimentally measured to 10 significant figures is like a lie, because it's not like their experiment. I mean, to measure anything to 10 significant figures experimentally is, inconceivably almost impossible, right? That's what makes it so impressive that they could measure this constant to 10 significant figures, but they really don't. It's like they just measured one frequency at 1 significant figure and then plugged it in some calculation, which came up with 10 digits, right? That's like saying,
I think you might find if we dig a little deeper that it wasn't an experiment at all. Basically, it's a computer simulation where followers of Feynman diagrams basically made all of the possible Feynman diagrams, which would give you the input and the output shown. And then they summed up all of these possible Feynman diagrams in a computer simulation to come up with this number. And people who are doing calculations, they'll often, get a huge number of significant difference, digits, I should say. But that's based upon some of their assumptions as being correct.
No, I'm trying to look at it here, and so far I still don't see what the actual experiment is.
I don't think there is one.
Well, they say that
All computer generated simulation.
well, they have a measurement. So they have a measurement of the anomalous magnetic dipole moment made by a group of Gerald Gelbrisi at Harvard University using an electron caught in a penning trap. So somebody's measuring something. So the difference between the electron's cyclotron frequency and its spin precession frequency in a magnetic field is proportional to G minus 2. An extremely high precision measurement of the quantized energy of the electrocyclotron orbits or Landau levels of the electron compared to the quantized energies of the electron's two possible spin orientations gives the value for electron spin's G factor, which is this 1.001 blah blah thing here. So they measured that.
We're really going back in time here.
So they measured that thing. And then they do a current state-of-the-art theoretical calculation of the anomalous magnetic dipole moment, blah, 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 leaves a more precise value of alpha, which is 137.035.
That's what I was talking about. In this paragraph here, it says the electron includes the QED diagrams up to 4 loops. That's what I was talking about, the computer simulation way to do the calculation.
So
but this is all history now. I mean, you probably won't find anything in there about that, the fact that the anomalous magnetic moment is purely just an experimental artifact, due to the fact that the constituents of the electron can act as a magnetic potential or an electrostatic potential with reference to other quanta flying by it, which is what is involved in any experimental measurement that they're doing. Plus the fact that they even have to use a G factor shows that their theory of continuous space-time is definitely, I mean, that's like a primitive tribe. I mean, it's like you're looking at a primitive tribe here. It's surprising Wikipedia would even repeat this stuff.
Well, I'm still looking for the thing that they've measured to like 10 significant digits. So, I mean, it's clear that they've made some calculation of what it should be. And then they're comparing it against some experiment that comes up with that factor directly. I mean, I can understand how that would work. So you make a prediction of the anomalous magnetic moment, and then you compare it against an experiment which directly measures that thing. Because that's the one here, a precise measurement of the anomalous magnetic dipole moment. And then 2, a precise calculation of that same moment. And then you compare the two, and then you see that one is very close to the other. Okay, I get that. But what is the actual experiment that measured the anomalous magnetic dipole moment? I don't see that here. Because like I said, I was thinking that when I actually was able to see what that experiment was, it wasn't very impressive. It was just like measuring one frequency or something, and that was it. You weren't measuring something to one part in a billion or anything like that. That's just like saying that
we might put our money on the table. We might put our money on the table and make a bet. In that long article that you're scrolling down there very patiently, I bet you won't find even a mention of the fact that the charge and magnetic potentials intrinsic to the electron can cause an artifact in the measurement, in any measurement involving electrons. I bet you won't find even a hint of that. Why? Because the anomalous magnetic moment is the artifact. And so you're getting a Nobel Prize for calculating how much the artifact is up to 10 digits. Wonderful.
Well, what do you mean by artifact?
Something which distorts your measured values from the true values. Whatever you're doing to measure something about electron behavior, this involves other particle or other quanta in its vicinity, and those are affected by the electrostatic potential elements and magnetic potential elements, which are constituents of the electron.
So I think in terms
I
of
bet you there's not
experiments,
even a hint of something like that in that article, because the whole thing crumbles to ashes. Now, in other work, in elementary particle work, people are extremely concerned about the fact that the electron contains charge and therefore is going to affect anything that you fire at it in a collider or whatever, and that's going to alter to some extent the results that you get. So that this article silence on that, where you can point to fields of particle research where this is a major concern. Like, how come the electron doesn't completely explode, for example, by its charged constituents repelling each other, and yet that's completely absent in that article. I would bet. I haven't read the whole article sentence by sentence, but you're doing a service here to put that up, frankly.
well, here's an article I found of somebody who's trying to measure the anomalous magnetic moment of the positive muon with a precision of 0.7 parts per million. So kind of wondering what exactly they're trying to do here. Let's see here. Dennis is trying to call me. I don't know why he's trying to do that in the middle of our conference here. But Dennis, if you have something, you can just put it in the chat and hopefully we'll get back to it. But I want to see what they're, so this is explaining what the thing that they're looking for, right? Great. Acknowledgements, experimental principles. Wow, this paper is long, okay. Magnetic moments, theoretical calculations, experimental principles. So they have a collection of longitudinally polarized muons injected into a storage ring where they follow a circular path, the magnetic dipole, rotating blah, blah. Okay, I can understand that. So they've got muons and accelerator. And the frequency is written as a 3-vector, blah, blah, blah. Centripetal, rotates that frequency. I think fundamentally they're looking for the frequency. The anomalous precession frequency is defined as the difference of the spin precession and cyclotron frequencies of the frequency at which the muon spin advances relative to the momentum, assuming the motion of the muons is purely longitudinal. Blah, blah, blah. So what did they actually measure? And Dennis keeps on trying to call me. Let's see here. So evolution of experimental precision here. I still don't see where their experiment here is. But there are a bunch of experiments here coming up with different values here. I guess it's the 11 point something here value, and they keep on improving the value. And their precision, so the number keeps on moving. But once again, what is their result here? So as the years have gone by, they've kind of narrowed in on what the value is. And then you see the error bars are getting smaller here. So I'd say all the experiments were kind of consistent, except for this one, the second one from CERN, which is off the chart. So this makes me kind of wonder, how is it that this has been measured to 10 significant digits when all the experiments themselves are off by quite a bit, right? You have that much experimental error. That's why I think this statement that it's been measured to 10 significant digits is just a lie. I feel it must just be a lie. My point being that it's like like measuring the accuracy of pi. You can measure that out to like 1,000 digits, right? Because it's just a calculation, right? It's a complete lie. But yet I still don't see what the actual experiment is and what they actually measured. I mean, there should be a chart in here showing some results, but if it's there, I don't know where it is. And that's just the frustration I have with this stuff, QED. You look into this stuff, the mainstream parrots this stuff that, it's like accurate to 10 digits. And then when you go looking for the thing, it's like, you can't figure it out. Yeah, you had something you're going to say, James?
Well, whatever the thing that they measured in the penning experiment, I guess, or the penning trap, I guess I should say, can't avoid the fact that whatever you're measuring, the electron constituents contain quanta, which have the attribute of being an electrostatic potential for the m bits and a magnetic potential for the L bits, which are going to affect quanta in neighboring locations in space, which is a cubic lattice, okay, and outside the electron. So in other words, the intrinsic elements or constituents of the electron are affecting what's going on around it. And that would normally in physics be called an experimental artifact, something which limits or affects the accuracy of our measurement of the intrinsic properties of the electron. But they're trying to say that this anomalous magnetic moment is in fact an intrinsic property of the electron, and they're using things like a factor of 2 in that equation. And if you look up Bohr magneton, you'll see that 2 is in the denominator. And in the equations you just showed, there's a G factor in there. And so so we're looking at history. I mean, there's not a whole lot of logic in what you're looking at, and so your complaints that you're not seeing what you're looking for. Well, in my opinion, what you're looking for is simply not there.
Oh, they measured something. I just want to know what or how.
Well, whatever they measured,
they have this gigantic
the
paper.
amount of the anomalous magnetic moment, which is an artifact.
Yeah, but their impressive accomplishment is to say that, oh, we measured that experimentally and we calculated it, and they're the same. And they're accurate to like 10 significant digits. The most accurate experiment done ever is, what they always tell you.
Well, you have to defend the Nobel Committee for awarding an award for this. I read somewhere, probably on Wikipedia, that I think Sommerfeld or one of the guys involved in the anomalous magnetic moment actually has the number inscribed on his tombstone. So this is what you're up against. It's called tradition. A more modern full quantization view of things would call it superstition.
Let's see here. Well, we've had Dennis. Dennis is here. Dennis, get up. Okay, you're on.
Okay, well, thanks. Yeah, you're right, Franklin. and the other gentleman is right too. It's experimental artifact in Dave Bergman and I's modeling. We get the exact right value for the magnetic moment, and the fact that it isn't the usual measured value comes from the fact that in order to measure it, you have to put it in a penning trap, and that means that it's held in a certain position by electric and magnetic fields. And but since the thing is not alone in space, the fact that it's in these magnetic fields alters the moment. And I think this is what Dr. Keene was saying too. It's just the reason they have to introduce the G factor is to take account of the fact that in the penning trap there's electric and magnetic fields which then alter the shape and spin and whatnot of the electron.
So what's
I agree
anomalous?
with Alan on that point. Alan, I think, is just talking pure common sense. And from what little I know of his work, he faces the issue of why the charge in the electron does not, scatter, and what holds it in place and so forth. It's a little different approach, but in many ways, it's a very similar approach to what I'm trying to do. But thank you, Alan, for that comment. I appreciate that, not being the lone guy saying this is a bunch of BS.
Well, it is a bunch of BS, unfortunately, and people are getting Nobel Prizes for BS. There's the Higgs fake. Now, if you follow ResearchGate.com, they're finding out that the gravitational wave detection people have all screwed up, and they got their 3 Nobel Prizes for supposed 2 neutron stars merging. I mean, this is like the cow jumped over the moon or something. It turns out that these signals are apparently coming from the solar system, the Earth, the moon, first of all, then the sun, and then Jupiter, which is the largest planet. It's huge. And they're tracking this down now. They've got charts and so on as to when these so-called detections occur, and they correlate them with the tides, which is how the Earth is affected by the moon and the sun and Jupiter, a large planet like Jupiter. And but the thing rolls on. They don't care, It's the great adventure of science. And once they find out that the gravitational detection was bogus, it'll be like Professor Weber's gravitational wave detection with big aluminum cylinders as antenna. Those cylinders, one of them is in the Smithsonian now, even though the whole thing was a bust, because it was part of the great adventure of science. And just the LIGO people, when it's found that their thing is bust too, will undoubtedly have their parts of their apparatus in the Smithsonian, and they'll be remembered for a long time as being great scientists. I mean, that's the situation nowadays. It's that bad.
Yeah, I've been to LIGO, and it's like miles long. So I'm not sure. Maybe they'll put part of the mirrors in the Smithsonian, right?
I beg your pardon?
I've been to LIGO here in Washington State.
Yeah.
And they have a very nice, fancy building, and you can see they're spending all their money on their building. And
they live high on the hog, don't they?
Yeah, they do. They have the nicest parking lot and visitor center.
And even though they're going to turn out to be a bust, they'll be celebrated in all the textbooks as part of the great adventure of science.
Yeah, for spending millions and millions and millions of dollars. That's
Billions
great.
of dollars.
Billions of dollars. Yes, that's great. We're doing
least
that.
hundreds of millions, but I think actually billions.
But by the way,
and
Plankton,
there's no way to stop this, I don't think.
LIGO, the mention of LIGO just reminds me that towards the end of last week's conference, we started to talk about Michelson-Gale, and we ran out of time. So I'm just wondering if either today or at some other stage, you'd like to give me maybe a few minutes just to say something about that and the subject of gravitational tidal locking and how it fits in with other experiments. Maybe 10 minutes max. I could just put up one or two slides.
All right. Well, let's continue on a little bit with our discussion on QED. And when we've driven that horse into the ground, and we'll get back to gravitational topics here. But let's see. Let me get back to quantum electrodynamics here. So I'm not sure what the precision test to QED is, or whether we should believe it or not. But it does touch upon a couple of, okay, there's the anomalous magnetic dipole moment. And we were looking at the quantum vacuum. So I want to talk a little bit more about the quantum vacuum and whether it's empty or not. There was some discussion about that. So James thinks that it's filled with his quantum qubits, or right? What do you call them, James? And I think that space is filled with actual physical positrons and electrons, is another way of doing it. Bill Lucas might think that space is just filled with electromagnetic waves. I think that would be his opinion, that if Cornelius was here, he would say that space is filled with tension fields entirely. So,
well, I think the mainstream are certainly engaging in what one might describe as doublethink. I mean, they admit that space has properties, that we can enumerate various properties, but then they say it's nothing, it's nothingness, it's a vacuum. That seems to be quite illogical to me.
Yeah, I think that's kind of stated in this sentence here, where it says it's not truly empty, but contains fleeting electromagnetic particles that pop in and out of existence. So this is as much as they're willing to admit that there's something there, but it pops in and out of existence, right? Just magically. And we were talking a little about the in the emails this week about the Lamb shift. And Cornelius was, I stated that, there are experiments that are indicating that space is, in fact, filled with a sea of charges, right? And the experiment that I had pointed out is this Lamb shift one here. So, of course, if it's based on QED, then I think that's the whole thing is hooey anyway. So, but they are looking at this experiment called Lamb shift, where they're looking at the energy levels are into two levels in the hydrogen atom, which is not predicted by the Dirac equation, which should have the same energy. So let's see here. So the effect was first measured by Lamb-Rutherford experiment. So they measured this thing. And what's the importance? Then we've got a bunch of the fluctuation in electric magnetic fields associated with the QED vacuum perturbs the electric potential due to the atomic nucleus. The perturbation causes a fluctuation in the position of the electron, which explains the energy shift. And then we got some Greek here. More Greek. And even more Greek. Okay. So this is all of the, we finally come across the fine structure constant. But what is the conclusion here? So you've got these things. And there's a one loop effect. I'm not exactly sure what that means. There exists a 0-point oscillation, blah, blah, blah. So that doesn't exactly explain what the significance of the Lamb shift is. But there was another article that I sent out earlier this week about the Lamb shift here. So let me see if I can bring that up here. So there was this article, and I found it still available on archive.org, which is a trick. So if someone sends you a link and it's no good, you can sometimes go to archive.org, plug that in, and you can recover the paper, which is what I did here. So this is a article here about the Lamb shift here. Let's see if I can get this a little bit bigger here. And they're talking once again about QED.
I'm not seeing anything, Franklin. I don't know if you've shared your screen.
Oh, have I not shared my screen? Okay, let me see. Let me make sure I share the screen here. Yeah, didn't quite do that. Okay, yeah. Keep me honest here. Okay. So let's see here. Where's my picture here? Okay, here we go. So looping through the Lamb shift. So the Lamb shift is also supposed to be a confirmation of QED. Right, because I guess they make these calculations, and nothing to do with sheep, and it has to do with two basic QED phenomena: self-energy and polarized vacuum. Self-energy effect occurs when electrons subjected to electric and magnetic fields spontaneously and randomly emit photons, and with an incredibly short time span reabsorb them through a technique called renormalization, aka cheating. QED theory provides a means to determine the energy of this electron self-interaction as a small finite correction to the energy that binds the electron to the nucleus. So now here's that topic of renormalization, which is how you take, you take infinity divided by 8 infinity, and 8 infinity divided by 1 infinity, and you get 8, right? So infinity divided by infinity equals some constant, and that's what basically renormalization is. It's like that is questionable. Maybe that gets back to what this original paper is, which is something that was rotten in the state of QED, right? There's something rotten in there. But let's see, the polarized vacuum effect involves pairs of virtual particles, one with a positive charge and one with a negative charge. Such pairs are created spontaneously from a vacuum in the presence of a positive or negative field, and then are polarized or aligned by the field's charge. For example, say a virtual electron-positron pair occurs in the presence of a positively charged ions. The virtual electrons drawn to the positive charge tend to align closer to the ion nucleus than virtual positrons, which are repelled by the positive charge. Thus, an electron that orbits an ion travels with fickle companions, swarms of virtual photons and electron-positron pairs, randomly winking in and out of existence. The Lamb shift is a tiny difference in the energy of an ion's electron between two quantum states that are otherwise identical except for the shape of the electron's orbit around the nucleus. Because of this dissimilarity in the electron's orbit in the two states, the electron interacts slightly differently with virtual particles, photons, positrons, and electrons that appear and disappear in quantum fluctuations. The resulting energy difference, called the Lamb shift, can be measured when the electron jumps from one energy to another. So let's see here. So, but generally speaking, they're saying that there's a sea of positive and electric charges, and as the electron is moving from energy level to energy level, the virtual electrons treat that charge differently, and they can measure that in these. I guess let's see if they got a picture of it here. No, I don't think they have a picture of it. They can yeah, they can get that. So you can kind of understand what they're doing there with the lamp shift. Although my question goes back to, what is the actual nature of space? So if these experiments is detecting this slight interaction of the electron with the surrounding space, and those things are positive and negative charges, and they're calling them virtual. They're calling that they're saying that these things wink in and out of existence. And I would say, well, why do you think they wink in and out of existence? Why not just say that they're just there? That would be my opinion. I would say that if you're measuring positrons and electrons surrounding everything, then maybe just empty space is simply just filled with those things. There's nothing virtual about them, and maybe they are actual real charges. So in my email this week to Cornelius, asking for, what is the evidence that space is filled with charges? And this is one of those evidences that space is filled with something, that something being charges, right? Now, we don't know exactly that that's a positron or electron, but mainstream seems to think they are. I mean, the electrons acting as if they were real positrons and electrons. As this electron is bouncing around the hydrogen nucleus. But
well, the paragraph, Franklin, that you read about, they're summarizing their vision of what's going on. I mean, is pure fantasy physics. This is just made up stuff.
Well, measuring the spectra of a hydrogen atom is not fantasy. Definitely, you can do that.
True.
So what's wrong with that?
I was talking about the paragraph that you read that was about 2 or 3 minutes ago on what their view is on what is happening. You got these virtual pairs, and then they're
virtual pairs
in existence. They're out of existence. I mean, we might as well go back to the work of Aristotle and Plato and start to take that seriously in terms of modern physics. It's just not credible.
Yeah, I don't think when they start saying things like such pairs are created spontaneously from vacuum.
Well, there's a word for that. They call it magic.
Yeah, I would say so. That's complete magic.
It's a magic show.
And I think anyone who thinks that must believe in magic or have a great deal of faith. But what do you think of the idea that what's out there in space is just a sea of charges, positive and negative charges? What do you think of that idea? Is that compatible with your theories that your quantum thing that
the quanta consist of in my work of two kinds of quanta: the m bit, which has the charge attribute, and it can be plus or minus depending upon its position, and the L bit, which are magnetic monopoles, much like the M bits are electrostatic monopoles, being plus or minus. The L bits have a direction, right or left, and so that gives you your magnetic monopoles.
But that still doesn't sound like a sea of charges. This experiment is pointing to there being a sea of positrons and electrons that the electron, as it gives us its spectra, is interacting with. That's fundamentally what the lamp shift is about.
Well, I'm distinguishing, I would like to distinguish between the quanta, which have a charge attribute. It's 1/3 of the elementary charge. It's called the fractional charge. And particles, which may be defined as assemblies in a local area of a number of quanta. And for the proton, there's a lot more of them than for the electron, which is much smaller. At any rate, so yeah, I mean, I'm not against the idea of a sea of charge, and it's also a sea of magnetic monopoles in about equal numbers, by the way. When you
Well, I
increase,
mean, if that would be okay. I mean, if space were just filled with these positron electron pairs, I mean, the positrons and electrons would be made out of more of your quanta. I mean, they're not, you know, your quanta, your fundamental. And you're saying that the electrons and positrons are made out of something, but do you see any evidence that that's the case, that space is filled with all of these positrons, electrons? The only reason why we can't see them is because they've paired off, they're just neutrally charged, or the whole sea is neutral. But nonetheless, from a material standpoint, they are there.
okay, you ask a very good question, Franklin. What comes to mind might be a little bit lame, but how about just the cloud chamber experiments or work observations? They're not really experiments, I guess, or well, they could be, where you can see what appears to be a positron and electron coming from one point and branching out and curving according to any applied homogeneous electric field. So there, would you consider that evidence that we can actually photograph these tracks in a cloud chamber and see these particles apparently emerging from a sea of plus and minus charge? Now, what I would be saying is that if there happened to be a convergence of quanta in a local area enough to raise the energy level of those what I call spots, which are spatial objects, to a high enough level to an adequate number of quanta composing them, then you're going to see in your cloud chamber an electron and a positron pair being, you know, spinning off from one point. And then you have to say, well, where did they come from? Well, they came from the so-called vacuum, which is not empty space. It's a sea of quanta, as my paper on vacuum composition seems to show. And if enough quanta converge on a particular location, which I call a spot, then you're going to have an actual particle which is visible in the.
But why would they converge? Once again, wouldn't that
How
be
about
magic?
random action? Why do any two things converge?
Random action. Well, I'm not sure that would be random action, but
the quanta are moving around all the time. Okay.
Because typically you'll see these things in accelerator experiments
all of the time. If by chance a number of these assemble in a local area, then you've got a particle, and you can see it in a cloud chamber. Now, I'm sure there's other evidence. You were asking for evidence. What came to mind is just the cloud chamber tracks.
Well, I would say that, you know, they don't sit there and just randomly assemble together, because intuitively, the particles that we see that make up the macroscopically observable objects of our world, you know, like a pencil, whatever, that does not come together as a result of random interactions. We like to think of our pencil being made out of, you know, tangible stuff, right? That stuff doesn't wink in and out of existence. There's an electron there, and it's always been there, and that is what makes up the pencil. And so if you see a track in a cloud chamber, it came from an electron that was like already there, is the usual conclusion. So this is how they determine whether, because there are other neutral particles besides neutrons or whatnot. And the way they decide that is that in the cloud chamber, they will see some particle decaying into some neutral particle, and then at some point that decays into two other, like, positrons and electrons. And the thing that they couldn't see between the two tracks, they figure is the neutral particle, and they give that thing a name. But definitely we wouldn't say that the positron electron came from nothing. It came from this other, neutral precursor, is what they would say. And I'm just arguing for the point. I'm not just discussing with you the possibility, because what we're really looking for is what is the real structure of space. Now, what is this Lamb experiment really telling us about the structure of space? So I'm arguing that this Lamb experiment is showing us something very important, which is that in what we consider the vacuum, and it'd be nice to know what the vacuum is, what's really there, is this sea of positrons and electrons. Now, I don't exactly sure what the format is. Like mainstream is going to say that this stuff just winks in and out of existence conveniently, right? Even though they have, no reason to say that it does. I mean, my response was they call them virtual because, well, that's the only thing they can call them, because they're so loath to admit what that's really telling them, which is that there is in fact a sea of real positrons and electrons. Because if you didn't call them virtual, then you'd have to call them real, right? And if you call them real, then they would actually have to be there. And if they were actually there, they'd actually have to be everywhere, right, in order for the experiment to work. And that would mean that all of space was actually filled with a sea of positrons and electrons, which is something they're not willing to admit, right?
Well, Franklin, let me try out an analogy and see how you react, Franklin. Let's say we could prepare a container of pure oxygen atoms, and it's not at 0 Kelvin. There's some kinetic energy. These atoms are supposedly moving around. Now, we come back in a little while and we realize that, hey, now we have oxygen molecules. 2 oxygens. Same way with nitrogen. So that's what I was referring to is so your virtual oxygen molecules are the oxygen atoms, okay? And yes, they're moving, and yes, statistically, going back to statistical physics, we can say there's a certain chance that 2 of these will collide in such a way that they become bound and form an oxygen molecule. End of story. So there's my analogy to quanta converging through whatever momentum they happen to have at a particular spot to form then an electron. So you might say the quanta, at least the M-type quanta, which carry charge, and particularly the negatively charged ones, are virtual electrons waiting to aggregate into an electron particle. By the way, all of this that we're talking about is related to gravity. In baryogenesis, my work shows that the quanta assemble themselves into the proton bit cycle and form protons. That's baryogenesis. And that happens at ordinary room temperatures. So that in a way, this aggregation process is related to gravity. If we think that gravity has something to do with things coming together.
Well, I don't think that really happens, because then we would have the spontaneous generation of hydrogen, because that's all you need to do to create hydrogen. Is if you can have a proton assembled itself spontaneously, then you would have hydrogen, because all it would take is just a spare electron, and there you go. That's all you need, right? So you're saying that hydrogen self-assembles?
Well, it does happen. Look at the universe. I'm not an astrophysicist by any means, believe me. But don't they say that hydrogen is the most common atom in the universe?
It is, but I don't think.
Well, okay. I mean,
if I created
it does form.
Well, I don't think if I had a vacuum, a really good vacuum, and I just waited long enough, that I would find that hydrogen has spontaneously appeared. I don't think that happens.
Well, you'd have to add the energy to make it appear.
I
And
suppose it's a
it
possibility,
will
but
appear. If you add sufficient energy, hydrogen will appear.
so you sit there and you zap it with like a whole mess of gamma rays and whatever, and your prediction is that hydrogen will appear. I mean, that's a reasonable experiment to do, I think, right? That in a highly energetic environment, that hydrogen will reassemble, or protons will assemble themselves. So I think protons are extremely durable. I don't know that we've seen them decay or be actually made either. I have to look that up. Like, how do you make a proton? Can you make a proton? It would be kind of interesting because I always thought that if you took enough positrons and electrons and mixed them at a 2-to-1 ratio, that would in fact result in protons. That would be my experiment, because I feel that protons are just 2 positrons and electron. That's what I feel. That seems to me the most sensible way to get a net +1 charge. This is just to add those things together. Let's see, we've got a bunch of comments, so let me see if we've got any comments here. And, you know, we've got Cornelius on the stream today. So, Corey, if you'd like to comment, I see you have some comments here. So we have a vacuum could be interpreted as devoid of focused nodal points of waves that define particles exhibiting the properties of mass. So yes, this is Corey's view that particles are this focused nodal point of waves. And we've been having we kind of been beating up on and ganging up against Cornelius on the emails, because we all tend to think that as particle people, we think that the hierarchy of physics in this area should be there's particles, and then there's attraction between the particles, and then tension is exhibited between those particles, and tension being at the end of the hierarchy there, not at the top of the hierarchy, as Cornelius puts it, right?
Well, yeah.
But, you know, that's everyone's
comment,
opinion.
or?
Everyone's free to feel however they want.
So do you want me to comment?
Yeah, go ahead.
Okay. So the particle being a focused wave, and the visibility of that type of wave pattern would be, like I've mentioned before, just a raindrop on the surface of water gives you a circular ring. It's a pilot wave type characteristic. And I've mentioned before that, you know, the particle in the energy form in that sense creates an inertial characteristic. You can prove that to yourself by, like I said, putting a bobber on the water and bobbing it up and down. And you can try to pull it before you bob it up and down, and you can pull it after you bob it up and down. And you'll notice that because of the wave characteristics that are focused around it, it will exhibit more inertia. It will be harder to move across the surface, because the waves themselves are pilot waves. They're maintaining its location. They're creating the mass, the inertial mass characteristic.
Well, I would say that, you know, waves are extremely important. But I would say that the waves are something that is emitted by the particle. It's like our theory, right. My theory and your theory would be exactly the same, basically, except that you're saying that instead of there being a hard little ball in the middle generating the waves, there's actually just a node of, you know, a knot of waves is what you're saying.
Your right? Theory is different in the sense that you're saying that the particle, the point, is this energy source for the waves. I'm saying
yes, exactly. The particle. Well, actually, the particle actually isn't.
Oh yes,
the source of the energy. Well, yeah. The thing is, it can't be, because if it were,
there you go,
then it would have to be. It would have to be its infinite source of energy, right? And that's not right.
That's right.
So
that's
the thing is that it has to get its energy by actually colliding with other things. There has to be kinetic energy present. That's kind of the trick in my theory, that I say that the wave that's coming off the particle, say the electron, it's a resonant frequency because of all the other electrons bashing into it.
Oh, you hit it nail on the head there. It's a resonant frequency.
Yes, it's a resonant frequency.
It's a volumetrically resonant region of tension within space. which comes to a focal point. That's why the waves, when they come together, they are resonant at that point because it is going above and beyond the tension limitations of the media it's traveling in. And that's
Well,
why
you
the
could say
wave,
that, or you could just say that
you could
the
just say
electron
that
is
the
ringing
energy
at its
comes,
resonant frequency.
yeah, you could just say that the energy comes from the point too, like you just said. And then
Well,
you
it
decided, oh,
only
it
in
can't
the
come from
sense,
the point.
only in the sense that you have to, in order to get a bell to ring, you have to hit it.
Right.
So
And in
this
order,
solves
in order to get resonance, you have to have a resonant volume.
yes, you have to have a resonant volume. So
Okay, so that point in that space is being stressed beyond the point of its tension capabilities, and therefore the tensions carrying capabilities of that point in space are being weakened. And when they weaken, the wave fronts will slow down. When they're strong, the wave fronts increase. And because of that, you reach a point of resonance where you go from a negative feedback to a positive feedback. And that is always needed in order to have a resonance. You always need to go from a positive to a negative feedback in all
I'm not
environments.
quite sure if that's, I mean, everything has
Well,
resonant frequency,
okay.
even buildings, human beings have resonant frequencies. Everything has a resonant frequency.
Yeah, and it's going from a point of being overstressed to understressed.
It has to do with the, certainly has to do with the stress, and has to do with the
that's where your resonance occurs at.
density and elasticity.
Right, and that's where resonance occurs at, where media becomes overstressed and positive feedback becomes negative feedback. So you're overshoot, undershoot, undershoot, undershoot. That's resonance. That's vibrations.
Yeah, but that is
so
a
that
property of material particulate
So that occurred.
things.
That occurred when space initially became stressed. Ether initially became stressed. It was stressed in such a strong manner that these resonant locations appeared throughout space because space is almost being torn apart. It's going way beyond.
Yeah, but that's like magic.
Okay,
It
so
takes
then
magic and faith to believe that.
From there, hydrogen atoms formed, and the simplest molecules have formed. And from there, you have gravity, which is stress, pulling those atoms together, pulling those molecules together, and making a gravitational environment under which the stress is very near this maximum tensile strength of the media all the time. And so it's very easy to create and combine these patterns into more complex molecules. Once they are extracted or ejected from this high tension area of space, they maintain their resonance, they maintain their shape. Okay.
Well, you're really talking about a damped resonance. I mean, you can have a resonance which continues with its positive feedback, and it just gets out of hand, and the whole thing, falls apart. Like, for example, a bridge where you have a troop of soldiers going over, get into resonance, and the whole thing goes down because there's no negative feedback element.
Well,
so you're talking about a damped system.
I'm talking about a volumetric resonance too, not just a resonance in something that's got a limited volume to it. We're talking about a spatial resonance, a resonance in 3 dimensions, for a compression into an expansion from a point, a stressing towards a point, and a stressing away from that point.
Yeah, but Ian brings up a good point that these resonances all have to be driven. Like, you have to have the active feet of the soldier on the bridge to keep the resonance going and to reinforce it, right? And that's where the point I was trying to make, which is that these things have to be driven.
And that's because the bridge is made of particulate media, which is actually a whole conglomeration of all these resonant points in space, making a composite that makes the bridge. Each one of these resonant points absorbs a little bit of the energy, which is friction, and therefore, because of that, you need to add more energy, because these little resonant points, which are particles, absorb some of the energy, and they eject the energy as radiant heat energy. And so they're actually transforming the energy. And because of that transformation of energy, you need to keep adding more to take away the characteristic of damping. This is the same as when I drop a raindrop on the surface tension of water. the raindrops surface will make multiple rings, but eventually those rings will die out. And the reason they die out is because the media that is carrying these waves is actually a particulate media that in itself is absorbing a little bit of these waves. Each one of these particles is
Yeah, well, I think
absorbing
the
a little
important
bit.
part is that anything which is emitting, well, which is actually, emitting something, whether it be sound or heat or electromagnetic waves, it's losing that energy out to the environment. Therefore, in order to keep on going, even if you don't consider things like friction, in order to keep those waves going, there has to be a constant input of energy at all times.
That's correct. And that constant input of energy is gravity and mass waves. They're spherical waves, the same spherical waves that create gravity.
Well, I would disagree with that. I would just say this.
I know you would, but the gravity waves, the longitudinal waves, are what's being focused. And once they're focused, and once that point of focus becomes so stressed that it cannot handle more energy, it will eject it as a transverse wave, as an electromagnetic radiant wave. So basically, you're absorbing it gravitationally, and the gravitational waves are maintaining this energy, but because it gets too much energy and it's going beyond the stress point that the media can handle, the stress is ejected as a transverse wave.
Okay, I know you keep on saying that, but it's just like I'll just have to say I don't believe it.
Okay,
so,
you're
fine to say that.
If I could ask a question to Cornelius, I think I heard you say that there's a particulate media that in which these waves occur.
No, that's not correct. That's not correct. I did not say that.
What did you say about a particulate media?
I said these waves create the particles. These wave patterns are the particles. Just like you take a surface of a pond, and there's nothing there but the smooth, continuum of the media, which is tensionable, the tensional surface. If you put a raindrop on that, or if you touch it with your finger, you'll get a wave, and that wave will emanate outwards. Now, in the universe, it works the opposite way around. The tension is created from the entire universe, and the wave tension is focused towards the point, but it's the point at which the wave pattern is focused that we recognize as a particle. So the media is not.
So the lifetime of a particle is infinite. The particles don't dissipate like
the particles can dissipate. They can dissipate, and they do dissipate, like an electron and proton pattern. An electron and positron pattern can dissipate because when they collide, when they come together and attract each other, in that process, they will eject a transverse wave, which dissipates out into space, into the rest of the universe. So particles can be created and can be destroyed, because particles are basically the focus pattern is a particle. Then you get into particles, virtual particles, which we spoke about earlier. If I take I asked in my response to Franklin, I've mentioned several times, he says, you live right next to the ocean, go study some waves. But the waves, basically, if I take a bunch of raindrops and I drop them on the surface of a pond, I have these spherical rings, but I also have interference patterns of the waves, as one wave from one pattern collides with another wave from another pattern. If you look at the ocean, you've got some nice rolling waves, but you also have interference patterns that come and go as peaks and valleys, and then just they're there and they're gone, because the waves are mixing and combining randomly, because basically you have waves coming from everywhere. And when
are you questioning the presence of waves? Because I love waves. Waves are great, but waves are all made out of particulate media. That'd be my point. It's like the
waves you can see are
every wave. Even the waves you cannot see. I assert have to be made out of particulate media.
Fine. Okay, that's fine. You could stick with your particulate media concept. It's not.
I mean, it makes sense. I mean, I stick with it because intuitively we see that, and we definitely have instances.
Okay.
Every wave that we can see is obviously particulate. Every medium, there is some question of what the electromagnetic wave is because we can't, see it. We're not sure whether it's particulate.
There's no question in my mind as to what it is. The question is in your mind because you're still stuck on the particulate concept. But that's fine.
Because that makes the most sense. It's most logical.
Well, that's fine.
It might help.
You're evolving.
It might help if our friend Cornelius could explain what his model of space is. What is the medium, if any, in which these waves he's talking about occur?
It's a tensionable medium, infinitely.
Yeah, it's just a medium.
Well, you've just given it
it's
a
a
name.
fundamental thing.
That doesn't explain it. Giving it a
No, it
name
doesn't. I mean, that's
is
who
just
his
giving it a
postulate is.
label. We call it labeling.
Okay.
Like
I mean,
girls at the grocery
okay.
store have this little thing where they can put the price on things and just stamp a label on.
So what's your bit act? What's your bit look like? What's your bit? Explain
It's
your
an
bit.
abstract concept that
There you go.
energy.
All right. Good.
I mean, that's perfectly fair. At some point, all of our theories have to break down into something which is a postulate, right?
What is tension energy? What is binding energy? What is the energy between these particles? What's pulling between these particles? What is the attractive force? What is energy?
Energy is matter in motion. We were also having this other discussion. Since some people think
matter
is energy.
What is matter? What is matter?
Matter is electrons.
What is electrons?
An electron is an electron is an electron.
Oh, an electron is a pattern of tension waves.
No, it's something we experimentally find being emitted from a CRT.
Rather than physics.
Cornelius.
It's a hard little ball.
I'm
That's what I
trying
think.
to help Cornelius explain basically what his postulates are. I mean, yes, a physical theory can have postulates. So he's saying a tension something or other. As far as I know, tension, in the classical sense involves, you stretch something. But he's just
a particular
So
medium.
what is your postulate, actually?
Tension is a measure of the binding energy. Is
Binding what to what?
The tension is the media. It's not a what to what, because if you have what to what, you have particles. You have distinction.
I think you just have to accept
So
that
there's
tension
a
exists.
media. Well, let's try and help Cornelius really explain to us.
Well, no,
what-
I don't think.
what
I
his
mean,
fundamental
you'll
postulate
never
is
get
here,
there.
because I think that would help me anyway to know what is fundamental. So he's saying there's a media that it has no particles.
Yes,
Well, then-
exactly. Media with no particles. That's what it is.
And yeah, but let's let him explain it to us, because I'd like to know what he's actually postulating here. And if there's nothing in this media, it would seem he'd have to postulate that there's something in the media in order to even begin to talk about tension. Or Cornelius is telling us that the whole classical idea of tension is completely wrong. And or if not wrong, that's not his idea of what tension is. So what is the definition of tension in a media that consists of nothing in it?
It's the binding energy that holds the media together.
The binding energy that holds the media, but what is the media?
The binding energy.
So you're really arguing as to what comes first. What is the actual cause? This is really the same as the mind-matter argument.
Definitely the chicken.
Shows it.
No, it's not.
And it can be quite quickly described in Bertrand Russell's terms as what is matter, never mind. What is mind, no matter. You could argue
that's not it. That's not it.
Well, I'm just trying.
That's not it at all, because if you get particles and you say there is a tension between them, there's an attraction between them. What is between them that's causing the attraction? And what are they made of?
Me, I would argue nothing. I
What-
mean,
what-
actually, they're
what-
being pushed
what-
together.
What are the particles made of?
Electrons and
We
positrons.
agree there's an attraction there, and we can measure it, and we can predict how it behaves, and so on.
What is that attraction
And
moving
that's what
through?
we can do. The rest is really speculation.
But what is the attraction moving through? So all I'm saying is that the particles are the focused intensity of the attraction, in the force. Particles are energy. They're tension energy. They're the strength of the force increases to such an extent that we notice that that's unique. And their particles are more than they're also a pattern of energy. They're a pattern of waves. Just like there's surface tension. If I look at the surface of the water, there is tension in that surface, and the tension is between every particle.
But you'll
between
never
every
get the tension in
between-
water to break down to look into something like a particle. That's it. Water tension doesn't break down like that.
No, tension doesn't break down. Tension is fundamental.
Your argument is that the immaterial comes first, whereas I think Franklin's argument, for example, is that the material comes first.
But the material
Excellent.
always,
Exactly. The
material
material
always,
comes
Philosophical
first.
argument.
but the material always requires a force between it. Always requires energy between it, because if the material doesn't have some kind of connection between it,
No, I think the material doesn't require anything. Material, electron, you could put a single electron
material
out in
electrons-
space, it would be
material-
perfectly fine.
material electrons are very complex or magnetic or electromagnetic wave patterns. They're much
No,
more
they're very simple, really. Science can't break them down into anything. They're the simplest things in the universe. They just have this mysterious thing called charge coming out of them.
It's not that they're simple and they can't because they can't be broken down. It's that they're very tightly bound together patterns of energy.
Or it could be that they're just simple, right? Well, actually,
No,
see, my
because-
stick is I'm not going to say what an electron is. I'm still looking for that answer to that question.
Well,
really.
and I've defined
I've-
I've defined the wave pattern that defines an electron.
I mean, but some people like you can't explain what an electron is, and that's kind of your motivation, because it's like if you ask me what an electron is, I'll have to say I don't know exactly what it is. All I would say is that I know what it does. I
have
that
defined
it-
what an
Yes.
electron is and why.
and you can define what an
an
electron is, and some people like doing that, but I disagree with your definition because I think whatever an electron is, I would say it's definitely not a bundle of waves.
But by knowing what an
I
electron,
know enough to know that that's wrong.
but by knowing what an electron is, and by knowing that an electron is a complex pattern of tension waves, then you can use that fundamental understanding of tension to discover why electrons repel other electrons and why electrons attract positrons and why the magnetic field
Well, that's the
emerges-
biggest problem
why
that I
the magnetic-
have,
why the
because
magnetic
if
field
I
emerges
think
from
that
an electron.
electrons are made out of these wave tension patterns, then I think they should go just right through them, because I know that is one of the main properties of waves.
But
They
we
do
already-
not collide with each other.
but
They
we
can't.
already discussed that.
Well, they interfere. Waves can
They
interfere.
interfere, but generally speaking, you get one wave going right at each other. They will pass by as if,
And we
wasn't
talked about that last week or the last time we talked as to what we already discussed that the waves, basically the particles, are tension energy patterns formed about above and below the maximum tension energy of the media. That's the
and there is
resonant,
no such thing.
that's the resonant frequency of the media.
There
Okay?
is no such
So
thing.
if you
I
haven't
might suggest something. Maybe, my interest here in the last 10, 15 minutes is to try to help Cornelius present his ideas. We have the right to postulate something and say, and if you ask us, why is that, what is a one state bit, that I've talked about. And I'm saying, well, that's just a postulate. I don't know beyond saying that it's a postulate. Perhaps Cornelius could make up a few slides or something and present what his postulates are. Apparently, he's postulating a kind of a space. His model of space has the property that it's able to, between point A and point B in the space, that it's able to exhibit a tension property. but that's my words. I like Cornelius to tell us what he's assuming and what he's postulating that can't be explained, that he does not even care to explain. It's just a postulate, and then get the results of his theory. That's what I would say.
Good idea. Good idea.
You already explained it. The tension is a measure of the point between A and B. But points A and B are not particles. Points A and B are just distances within space that are measured by the time it takes for the propagation of a tension wave to move through it. That's how we measure distances. We measure space by the patterns of between the patterns of tension within it. Just like when we have two raindrops on the surface of the water, we measure the distance of how far those raindrop patterns are from each other by the relative size of each of the patterns to a third pattern. And so
what I would expect in a coherent presentation of Cornelius's theory is a good argument, or some comment as to how completely empty volume, defined geometrically here, is a volume that's got a height width.
There's some recordings already on
can have
CNPS. You can go back and listen
tension
to them.
between points A and B in it, which is contrary to all known physics that at least that I was taught as a little boy.
When I was a little boy, you were taught about tension between particles. You're still stuck on tension between particles rather than what makes the particles.
Yeah. Although I think
that's why I like
I'm
the
describing
presentation from Cornelius. We start with this postulate or assumption, which we're not going to explain. We're just going to say it is that, and from that we get all of the rest of Cornelius's thought pattern.
It is that.
Right. Yeah, I think Cornelius has, I think you did a good explanation. I mean, we're talking from fundamentally the postulate that there exists this tensionable medium, which is non-particulate, right, Cornelius?
That's correct.
That's correct. So that's the main postulate, right? So he doesn't have to explain that. That's just what it is.
But then I explain. Then from there, you can explain everything by how tension works.
Yeah. So you explain that you got the tension, you got the waves through there.
Do you understand how tension works? James, have you listened to any of the discussion about how bubbles interfere or interact with each other, or how
that's getting into something else?
I've been here for the last several weeks. I don't recall that.
No, that was very much earlier on. Although we're getting back to we got about half an hour left in the conference here.
That was before I was born.
Yeah, that was before you were born.
Franklin, can you connect James up with the CNPS conference that I spoke at, and I did some drawings on, and I demonstrated how bubbles attracted each other and how the tension interacted with each other, and we can expand from that onto how bubbles form, how bubbles are linked, characteristics of bubble.
Well, I'm still not quite sure myself that isn't at all, convincing.
Could you just direct James towards that so he can decide for himself?
But generally speaking, all of our presentations.
Send me the link, please, Cornelius.
All of our presentations.
I recommend a very simple
at Gmail.
James, I recommend a very simple experiment for you to begin with.
All of our videos are on YouTube.
Watch a couple of bubbles on the water and watch what happens when they get closer to each other, and explain why those bubbles are being attracted to each other, and explain why there is a change in volume. Basically, just look at that video and just look at a couple of bubbles and observe the fact that when there's some bubbles on the surface of water, as they approach each other, they get closer and closer together. They will attract each other at a greater and greater rate. They have a gravitational characteristic that's due to the tension in the surface. Okay? And that's where the fundamental of tension is demonstrated. And from that, you can just look at the tension in a wave shape and not just a bubble. And because you can look at how tension in one wave will affect the tension in another wave, and how waves will begin to move in different directions and reform themselves because of interaction with other waves. As to why these wave patterns reject each other and why two things appear to bounce off. The tension in the media has a limitation. It's a nonlinear tensionable media. You reach the maximum tension point and it turns around and it becomes weaker. If you stretch any tensionable media, stretch a rubber band too far, it will break. If you stretch the tension of the media that's carrying these waves too far, it will break. If the media breaks, where can the waves go? They can no longer go towards each other. They will be reflected off of that broken boundary.
Okay, here's something that I'd like to see Cornelius work out. Given his postulate that space is basically attentionable media, give me the value for what its intrinsic tension is.
Okay.
I mean, there are units. Tension is. I don't recall the units. I'd have to look that up in my physics 101 book. But
James,
I'd like to see a number as to what empty space or perfect vacuum or whatever you would call it. What is the intrinsic tension of this?
James, just let me stop you, okay? I've got to go here. I've got an appointment.
Stop me.
I'm telling you right now, I do not do the math. Okay, I have these theories, and I do these experiments that show that that's how tension behaves. The mathematics will come in time when somebody has the time or a desire to do the mathematics, or I'm ready to retire soon, and I may go to school and relearn the higher level mathematics that's required to do this modeling. But right now, the math is not there. So asking for numbers is not going to do you any good.
So it looks like you got a fan here, Monsieur. You know.
I do have to go though. I have an appointment.
All right. Well, thanks, Cornelius.
Okay,
so, as I said, all of our science chats are available on YouTube. Just search for John Chappell Natural Philosophy Society. A lot of the earlier ones are all indexed. So probably if you search for Cornelius's name, because we did give him like a whole science chat once, and he did go and try and sketch out the basics. Although it's only the basics. Unfortunately, Cornelius does not have any papers or websites or anything written down. So the primary source of things from Cornelius is actually emails, which you can find in NPA relativity on the NPA-relativity group on Google Groups. So if you want to go find out what Corey is writing there, he's very frequent participant there, or check out the science chats. Now, let's see. Now, I promised I'd get back to Ian. Okay, so let's get back to Ian. So Ian, let's talk gravity. What were we talking about last week?
Well, I'll try to get this maybe without absorbing too much time. I just have maybe one or two slides, and I have the original paper of Michelson Gale. So let me
remind us about. We were talking about the whether you can detect the speed of the Earth, right?
Yes.
Michelson Gale can detect the 24-hour rotation of the Earth, but not its orbital period around the sun. Basically.
So the basic things we could talk about is just these are just some slides from the presentation I made in Russia in 2004. The Michelson-Morley truth and Noble experiments are actually approximately null, but only if we're trying to measure the Earth's orbital speed. However, the Sagnac experiment is positive for the spinning disk, and accurate experiments, we could talk about the Michelson Gale, etc., show light speed on Earth is dependent on the rotational, but not the orbital speed. And I explain that in terms of inertial frames, Coriolis acceleration, and gravitational tidal locking. So that's more or less what we were talking about, I think, Franklin. Now, I thought the best way, actually, can you share my screen, by the way?
I can't share yours, but you can share your screen, At the
Okay.
bottom, there's a little button called Share Screen. And when you click it, it will put up another dialog, and you need to click on Share Screen.
Okay.
And then it'll put up like a picture. It says like your entire screen. You need to click on that picture of your screen and then click Share, and then you can share.
So I was talking in vain a little because I had a slide up there. Share your screen. Okay.
Go to Share Screen.
Well, let me get the slide up again. So that was the slide I just talked about. I'll maybe mention about those 3 or 4 points there.
Yeah, I was a little confused about that, but I didn't know that you were going to get around to showing the slide.
Yeah,
so
sorry.
let's get you to show the slide.
Now, can you see this paper up on the
I
screen?
cannot right now, so you're not sharing right now.
Hmm.
You need to click on Share Screen. It puts up
thought
a
I-
dialog.
You have to click it again, maybe. You do it,
And then you
click
have
there.
to click inside the dialog on the picture of your screen.
Oh.
And then click on Share Screen.
Oh.
There's that middle little step that everyone forgets. There you go.
Yeah.
Now I can see your screen. I can put your,
So
I can
the
add
slide
your
was,
screen.
third time lucky.
Okay, there we go. Now we can see it.
Okay. So I have maybe 3 slides. That's the first one. It's just a summary. I'll just talk about the Michelson-Morley Troughton-Noble, which is the electrical analog of it, showing it doesn't show up the Earth's orbital speed anyway. It might show up a very small diurnal effect. The Sagnac does show a positive effect for a spinning disk, which is a relatively modest speed. And accurate experiments actually do show up the rotational, but not the orbital speed of the Earth, the diurnal rotation. And I explain this in terms of inertial frame, Coriolis acceleration, and gravitational tidal locking. Now, this is Michelson-Gale, and it's sometimes called the Michelson-Gale-Pearson experiment because they had assistance of Fred Pearson. And it was actually quite an interesting. This paper is very, very short. It's only a few pages. He doesn't go into a lot of detail. He just says what they did, and he says it's compatible with either ether theory or relativity. He doesn't go into much detail. Anyway, they set up this rectangular tract. It was actually about a mile in perimeter. I think I said the longer leg was a mile long last week, but it's actually the perimeter is about a mile long. In a cornfield southwest of Chicago City, in a place called Clearing, Illinois. Now, let me see now if I can get the next page. Yeah. So this is basically just a diagram of what they did. It's on its side, but so you have these are evacuated pipes, by the way. There was a vacuum pump which reduced them to practically 0. The sort of 12-inch pipes, and the light is going around one way, and then it's going around the other way and being recombined in the normal way. Now, in the Michelson-Morley experiment, you turn the table or you turn the apparatus through 90 degrees to get the difference, which is really twice the difference. So that gives you a sort of a 0 point. And in the Sagnac spinning disk experiment, you merely just stop the disk and you find where the fringe shifts are, and then you spin it in various directions. Now here, Michelson and Gale couldn't obviously stop the spinning Earth. So what they did is they built a very small subsidiary circuit here with practically 0 projected area, so that would be your fiduciary point. That would be your effectively 0 point. And then the long circuit would be the effect you're trying to measure. Okay, so that's just the apparatus. Now, the next page, well, that just gives details of the mirrors and so on, and the monochromatic light and so on. Now, okay, so by simple classical physics, you work out the Sagnac formula, which basically gives a fringe shift of that nature. That's the enclosed area, the wavelength, and the speed of light. He calls that v. Yeah, the velocity of light. Now, that it's the sine of the latitude, which is basically the cosine of the co-latitude. So it's effectively the projected area of the.
So if you want us to see the formula, can you zoom on your page a little bit there?
Zoom in. I didn't realize how small it was. Okay, I'll try doing that. Can you see the formula now?
A little bit, one more. There you go. Yeah, we can kind of see it now. One more.
Okay, because it looks great in my thing. So so that's quite simply the Sagnac formula. It's simple algebra. 4 times the area times the angular frequency of rotation of the Earth in this case. Phi is the latitude. So the reason you have sine phi, it's the cosine of the co-latitude, which is basically the projected area onto the plane of the Earth, which is spinning around the its axis, perpendicular to its axis. The wavelength and the c, their c is that he calls it v, is the speed of light. So I'll just zoom back so I can get to the next page now. Just give.
Well, you don't have to unzoom. You can just.
Okay.
While it's that zoom.
Oh, can I? Well,
I think so.
Well, anyway, I think it's just 2 more pages, which gives the results. Now, here are the results. So basically, they had all these observations of 20 measurements per observation, and they varied a bit here. And the mean value was 0.230 of a fringe shift, plus or minus 0.05. So now that's all very, very neat. But I do have to show you the last page, which does show 1 or 2 anomalies. So most of his measurements were indeed around this area, but they got some measurements which were near 0 and some measurements which were twice the value. So maybe they were experimental errors, or they had different operatives measuring at different times and so on. So if we sort of take the main value, 0.230 is the fringe shift. Now, I talked about this business of tidal locking, and I also referred to a gentleman by the name of Agathan Gelidis, who published in May-June 2001 Galilean Electrodynamics, Implications of Halfway-Keating, Michelson-Morley and Michelson-Gale Experiments. And so if you look at, if you consider that maybe you shouldn't get 0.230 of a fringe shift, you should get you should get a slight difference from that, because yeah, well there you are. See, if you calculate the value using the formula, you get 0.236, but we observe slightly less than that, 0.230, which is about 2.6% less. Now, if that is a real difference, well then there isn't 100% slippage of the Earth through the ether in its diurnal rotation, because let's say there's a tidal locking of this ether because of gravitational effects to both the sun and to the moon. Now, let's just calculate that. So the angular frequency of rotation of the sun, the apparent from the Earth's point of view, is twice pi radians, obviously, per 366.26 astronomical days. So that's the amount that the sun appears to move in a day, and the moon is twice pi radians over 27.4. That's the lunar complete cycle per astronomical day. Now, if we weighted the two, the gravitational effect of the moon is 2.18 times that of the sun. Because it's much nearer, so it shows the difference in the gravitational pulls from opposite sides of the moon has got much greater. So if we calculate something like an equivalent ether angular speed, which is the angular speed of the sun plus 2.18 times the angular speed of the moon over 1 plus 2.18. So that's just a weighting. What you get is you get twice pi by 0.026 radians per astronomical day. So in other words, you get, hey presto, 2.6% locking of the per day of the ether, which accords perfectly with this calculation here. Okay, so maybe I'll just complete it now by going back to the slides, because I have two more slides.
So your main point is that we have that the rotation of the Earth is not perfect through the ether. It is short this 2.8%, which you were able to calculate.
Yes. Now, so just very briefly, I have two slides. One is Michelson-Morley into interferometric systems, which is a second order in V over C. So it's very hard to measure effects because obviously V is very small in comparison with C. The formula is there, and you can talk about the various experiments. Some of these experiments have shown up some effects. The most famous would be probably the Miller ones between 1921 and 26 on the top of Went Wilson, ostensibly to reduce the what he considered the ether sort of being bound to the Earth. And Shankland actually et al. In 1955 tried to explain away Miller's results as temperature effects. Now, there's a bit of a scandal possibly there because Shankland was a pupil of Miller's, and Einstein had said that if Miller's experiments were correct, it threw out his whole theory. And Shankland became quite a relativist, and he made a career in it. And a lot of Miller's original results seem to have disappeared, and Shankland had custody of them. Anyway, I'll leave that. There was then Kennedy and Thorndike did a similar experiment on unequal arms of an interferometer, and the Ives-Stillwell experiment seemed to show up maybe a variation in the speed of light. Then in 1963, you had, masers used by Jasija et al. And the Brilton Hall experiment seemed to show nothing up. But Aspin did an analysis in 1981 and it showed that this Brilton Hall experiment showed up the diurnal rotation of the Earth. Then I contrasted that with the Michelson-Sagnac interferometric experiments, which are much better experiments because they're a first order in V over C, and you can see the formula that I showed up earlier is really the same as this. There's no sine phi in it, but that's basically it. Sagnac, of course, in 1913 got a positive result just by a spinning disk. The Michelson-Gale experiment in 1925 we've talked about, and Dufour and Prunier in Paris produced results where intermediate on a sort of a Sagnac experiment, they shone the rays of light on the disk into various areas in the laboratory and then shone it back, and they got no deviation. So it appeared that the disk wasn't actually dragging any ether; it was moving in the ether in the frame, the ether frame of the laboratory. Dufour and Prunier's experiments didn't seem to get promulgated very much. And one theory is that Paris at that time was occupied by the Germans, and you couldn't really get his results out. So the results were sort of stymied in time at that point in time, and maybe many years later they were not of interest, but they're important. And then there are later ones using ring lasers, and the Bilger experiment and in New Zealand, where you get the rotation showing up in the opposite direction. And this is the whole principle of the optical gyroscope for navigation. So I think, Franklin, perhaps I'll stop sharing now, just to indicate that is what I briefly mentioned last week, that the even though the speed of the Earth in its orbit around the sun is 100 times or something that of its rotation, it is not the speed itself. comparing rotation about a common axis with center in the sun, but it's actually the Coriolis effect, because the difference in the centrifugal forces would only be about a factor of 3 to 4, which is not a significant difference to mean that there's almost zero effect in one case and there's almost 100% in the other case. But it's the Coriolis effect, and you can look at things like Foucault pendulum, which you see, you can measure the Earth's rotation in the day because it knocks down bricks after a while, and it seems to precess. And similarly, you have atmospheric effects in the atmosphere, high pressure and low pressures, which are dependent upon whether you're in the north hemisphere or the southern hemisphere. So basically, that's how I explain it. And the slightly novel thing is that this 2.6% locking gives, what it tells, a 97.4% slippage of the Earth through the ether in its diurnal rotation. So I leave it at that. But if there's any time for questions, we can take them or maybe talk about it subsequently.
All right, thanks, Ian. And it looks like you've taken us to the end of our time here, basically. So let's just summarize a little bit. So we started off by talking about, something stinks in QED, pretty much, right? So we started with, let's see here, this, we have our papers here. So something stinks in QED, which led us into an investigation of what QED actually is. And so we were going and looking at what we can find in the source of all truth, which is the Wikipedia, about what QED is, and that led us into a discussion of what the quantum vacuum is and what the mainstream thinks of it, which is it's empty, but it's not empty, right? Which is, as Ian mentioned, double speak, right? It's like, well, what do you mean? And that also led into a discussion of what space is made out of, and what the lamp shift experiment was trying to show. And so that also led into a little a discussion on a comparison of models about what space could be. So like I would argue that space is made out of the sea of positrons and electrons. I was trying to see whether that would be compatible with, say, James's conception of his bits, and then comparison to, say, what Cornelius might say, which is his tensionable medium. And we got a little bit into what would be the fundamental postulates involved in that sort of thing. So after we beat that into the ground, then we did have a little discussion about what does it mean for the Earth rotate around, and Ian brought up his paper showing that that we detect like 97% of the rotation, and then there's this 2.5%, 2.8 or something percent that are not quite explained, but that can be explained through this tidal locking calculation, which I'm not quite sure I understand. But it's interesting that that it just matches up, right? Because it could have been like way off, but it seems to be within the realm of believability. So, but that would do it for this episode of the Science Chat. As I mentioned before, if you're interested in what Cornelius has to say, I think you should be able to scan through the Science Chats of the past year, and you should be able to find, hopefully indexed somewhat, the chat. Now, these new chats being done here on StreamYard, I generally don't put a descriptive index on it. And so it's kind of why I always try and do a summary. So if you want to find out what we're going to be talking about for the next 2 hours, you can probably just skip to the end where I summarize what we're going to talk about, and then try and figure out whether you want to watch the rest of it, I suppose. So little hint for those of you who are watching this on YouTube and might want to look at what we've discussed in the past, because like I said, I don't index or put a description for these new talks. But the previous talks, I did try to go back for a year or two to actually put the basic descriptions of what we were talking about. Okay, well, that will do it. Thanks for everyone participating, and thanks for everyone who is watching on YouTube and Facebook. But we'll see you next week then.
Thank you.